started. So let me just go over once more. This is the web page, which will be having all the information. And this is the team join code 278B5 of. So if you join it using this team code, you will be able to see all this information. I talked about some of this information already, especially the grading part. And about the reference, I was mentioning this is the textbook, Williamson's Monash, and also Vijay Vajrani's book is another option. There's also a lot of online courses which you can follow. For example, Coursera has courses by Claire Matthew on this topic or Mark DeBerg on this topic. There are a lot of other courses elsewhere which you can follow. So you can learn as you wish, but we'll also provide this lecture, like handwritten lecture notes which you can read. But either you can read this book or this book. That will be sufficient for most of the part of the courses. But there are some parts for which we'll follow some other resources, and for them we'll mention when we'll cover them. For example, geometric approximation algorithm we might cover. For that, we'll probably follow some of the notes from this course by Timothy Chan, or linear programming we'll cover. Maybe we'll follow something from this Tim Ravgaran's lecture notes and so on, but we'll mention them. But mostly we'll follow this book. Okay, fine. So any other question about logistical issues? If not, let's start. So this course deals with optimization problems. Now, what is optimization problem? Roughly, I am giving a very informal definition. Basically, you have some problem where your goal is to find the best solution out of some feasible solutions. And this kind of optimization is omnipresent in life because we are trying to minimize cost or maximize profit. For example, maybe you are planning to go for a trip to Goa, but there are a lot of constraints like the flight ticket, there is this hotel cost, there are food costs, and you're trying to minimize this cost. So you're trying to optimize the cost there or maximize profit. Maybe you're packing your bag for the trip, but you have limited amount of space, 23 kg. So you want to pack as much items as possible according to their utility within this weight limit. So you're trying to maximize profit within the weight limit. So this kind of optimization questions are we come across very frequently. But the problem is many of these problems are very hard. So if you're, let's say you're in a job and your boss gives you a job, some problem to solve, and you find it's very difficult, and you're not able to get a good algorithm, good efficient algorithm for the problem. So what are your options then? So one option is you can just go and say, okay, I cannot find any algorithm because I'm just too dumb. But then you will get fired. Other option is if you're too smart, then you can show, okay, I cannot find an algorithm because there is no such algorithm possible. But it turns out it's very difficult to prove that either. For a particular problem, there is no polynomial time algorithm. How do you show that? That's a very hard question. So if you're a graduate student and your advisor tells you, okay, solve this problem, what excuse can you give? So maybe you can give an excuse like this guy that, okay, I could not solve this. I could not find this efficient algorithm, but neither of these famous people. The person on the right is Richard Karp, and he is the person who started this area called NP completeness. So Karp introduced this area called NP completeness and showed that unless P equal to NP, the optimization versions of many of the problems do not admit any algorithm that simultaneously follow three properties, that you are finding the optimal solution in polynomial time and for all instances. So these are saying in engineering that you cannot have all three, fast, reliable, and cheap. You can choose only two. So here also you cannot have all three. You have to choose only two. Either the optimal solution you find, but then it will take too much time, or if you can settle for near optimal solution in polynomial time for all instances, or you can find optimal solution in polynomial time, but not for all instances. You cannot have all three together. And these 21 problems are frequently observed in many practical situations. So, for example, SAT is one problem, 3-SAT, then integer programming, vertex cover, traveling salesman problem, partition, max cut, knapsack, Steiner tree, hitting set, and many of these problems we'll see in this course as well. So all these problems are NP-complete problem, the decision version of the problem. So decision version says that you ask a question that whether something exists or not, yes or no question. Whereas in optimization question, we want to find an item under some constraint and want to maximize or minimize the cost, or maximize the profit or minimize the cost. So in this course, we'll learn a lot of approximation algorithms for this kind of problems, which are NP hard. So let me just go over briefly about optimization versions of this kind of NP-complete problems. But any question till now? Yes, feel free to stop me at any point if you have any question. Yeah, there is some question. Okay, so one example is 3-SAT. So 3-SAT talks about some kind of Boolean formula, whether it's satisfiable or not. So that's a decision problem. In the optimization version, what you want is you have some clause, some multiple clauses in CNF form, and you want to find an assignment which satisfies as many clauses as possible. Just max 3-SAT. So if you don't know about SAT, okay, fine, we'll come across this later, but it's an example. I will define what is this problem later in the course. But if you know about the decision problems, you can see the decision problem is just yes or no variant, whereas optimization question tries to find something maximization problem or minimization problem. Similarly, 3 coloring is a problem that given a graph, can you color all the edges, all the vertices using 3 colors such that for all edge, both endpoints receive different colors. So that's a decision question, yes or no. But in optimization, you can have multiple questions. For example, you can try to color it using as few colors as possible. So not 3, but maybe 4, 5. Can you do it using some minimum number of colors as minimum number of colors as possible? Second question could be, okay, you color with 3 colors, but maybe it's not possible to color all the vertices using 3 colors to have this legal coloring. But you make it as legal as possible. So you want to maximize the number of edges which satisfy this legal coloring, and so on. So there are a lot of other problems we'll come across in the course. So the problem is, I mean, these are NP-complete problems, NP hard problems. It's optimization versions. But you will come across these problems in practice. So what can you do? If you just say it's NP-complete, that's not sufficient. So what you can do is you can have approximation algorithm for the problem. So as I mentioned, there are 3 things which we cannot have together. So we settle for near optimal case for the first constraint. We try to find the near optimal solution for the problem efficiently. That means in polynomial time of the input size. And third one is for all instances. Okay. So what is approximation algorithms? So our goal is to solve, let's say, NP hard optimization problem, and we know there is no polynomial time algorithm for this. If we run exponential time algorithm, there is some theory, but it's too slow, and there is no lower bound. We cannot really prove a lower bound for this. If we use heuristic, some random or arbitrary heuristic, if we try out, it's fast and easy. But then the problem is there is not much theory, maybe, or maybe you're not able to prove any guarantee. The approximation algorithm is nice in that way that you can actually develop rich theory for these problems. And also you can show some good lower bounds under some assumptions. And when I talk about running time, polynomial, exponential, this is the thing I mentioned. So let's say n is the number of objects in the instance, and the problem might have some numeric data. And let's say you're talking about some graph problem. The number of vertices is an object. So there are n vertices in the graph. But edge cost or edge capacity, there are some numbers. The capacity is 10 or 15 or 20, some numeric data. And B is, let's say, the maximum success number. So by exponential, we mean something like 2 to the power n or n times B. So here I write B because B is a numeric data, let's say 50. So then 50, we represent in binary as log B number, like this data B will be represented in binary in log B number of bits. So actually this capital B is exponential in terms of log B. So n times B is actually exponential, it's not polynomial, because B is already exponential. Log B is the polynomial. The input length is log B, whereas we are running it in B. And when you talk about polynomial, it's n square, n to the power 100, n times log B, and so on. So any question so far? Okay. So before starting, again, remember why we are studying approximation algorithm. We need fast solutions for practical problems, and we need some mathematical rigor to study and analyze heuristics. If you propose an heuristics, why it works, you have to give some analysis. And also it gives a metric for difficulty of different optimization problems. We'll see different NPR problems can have different approximability. And it's a very cool area. It has a lot of it has developed a lot of rich mathematics. We'll see them. It's really fun. It's a puzzle solving kind of a area, which is really fun to study. So first we start with the definition of approximation ratio. How do we quantify an algorithm, the performance of an algorithm? It's by approximation ratio. So approximation ratio or approximation factor or approximation guarantee, we define as follows. So first we start with some optimization problem pi. Let's say 3SAT or some max cut, some problem. And we take one particular instance I for this problem. And okay, for should be pi actually. And then we define opt pi of I is the value of the optimal solution on this instance I. So given this instance I, what is the optimal solution? So this will take maybe exponential amount of time. But let's say we know that. So that is the optimal value. And then we are given an algorithm A that we run. And we have to find what is the performance guarantee for this algorithm. We call this algorithm A is an alpha approximation algorithm for a minimization problem pi if AI is less than equal to alpha times opt I for all instances I. So AI is the solution, the value of the solution written by the algorithm A on input I, and opt I is the optimal value for this instance I. So already it's a minimization problem. So opt is less than AI, less than equal to AI. What we want is AI should not be too far from opt I. So it's upper bounded by some alpha times opt I for all instances. And you want this alpha to be as small as possible. You know that, okay, if it is NP hard, we don't expect alpha to be 1 for a polynomial time algorithm, but we want alpha to be as small as possible. And typical values of alpha could be 1.5 or 2 approximation, like 2, alpha equal to 2 or constant or log n or 2 to the power n or something like that. And usually we'll omit this pi and I, and when we talk about opt, that just means that for this particular problem, for this particular instance, what is the optimal value? And you can define similarly the same things for maximization problem. So where your objective is to maximize something. And there, in that case, opt is greater than equal to AI. It's a maximization question. So what we want is AI is not too far from opt. So AI is upper bounded, is lower bounded by 1 by alpha times opt I. So in some literature, I mean, in this particular definition, alpha is greater than equal to 1. So alpha is greater than equal to 1. But in some literature, you will find alpha is defined to be less than 1 for maximization problem. So in that case, actually, this, instead of writing this as 1 by alpha, they use alpha itself. And then in that case, if you have this kind of expression, half times opt I, they might say it's 2 approximation. But in our case, they might say it's half approximation. But in our case, we'll say it's a 2 approximation. So if it is alpha is more than 1 or less than 1, based on that you can see, like the definition is either the definition like this one or the definition like this one. Okay, so is the definition clear? So in other words, you are trying to get the worst case ratio of AI by opt I over all instances I. That ratio is alpha. So this is also known as absolute approximation. So we call alpha approximation by default, but this is also known as alpha absolute approximation. And we'll see there is something called alpha asymptotic approximation as well. And as I mentioned, the different NP count problems, they are kind of equivalent in terms of the hardness, right? So decision problems, if you solve one of them, you can solve all the other problems in NP complete class. But the optimization versions of these problems, they can be quite different in terms of approximability. So we'll see for some problems, actually we'll not be able to get even, let's say, n to the power 1000 approximation, like in traveling salesman problem that we'll study next. But for some other problems like knapsack, you can get as close to 1 as possible. So given some constant epsilon, any constant, it can be like 0.0001 or any constant, you will get 1 plus epsilon approximation in time which is polynomial in n and 1 by epsilon. So as epsilon grows small, this runtime increases, but for constant epsilon, it still remains polynomial runtime, and you get as close to 1 as possible in the approximation ratio. Any question till now? So now let's go over some other definitions. So what is the best you can do in terms of approximation? So one notion is called PITAS, or polynomial time approximation scheme. So for a minimization problem, we call it admits a PITAS if for any constant epsilon, non-negative epsilon, we have this property that the algorithm is 1 plus epsilon approximation, or for all instance I, AI is less than equal to 1 plus epsilon times optime. And the runtime we need require here is polynomial time. So typical runtimes are like this, which is polynomial in input size, so n by epsilon or n to the power 1 by epsilon. So for constant epsilon, this is also a polynomial. And we'll later see there is something called APX hardness, and if some problem with APX hard, it does not admit any PITAS. So for now, you can ignore, but just remember this thing that there's something called APX hard, and if you want to show the problem does not admit any PITAS, you can show the problem to APX hard. Then you can have another type of PITAS. So this PITAS that we talked about, the runtime is quite bad. It could be quite bad. It's n to the power 1 by epsilon to the power 1 by epsilon. And for even small epsilon like 0.01, this will become n to the power 10 to the 100 to the power 100, which is a huge number. So one way is defining this thing called efficient PITAS, or efficient polynomial time approximation scheme, or EPITAS, where the runtime is slightly better. So now the runtime is some function of 1 by epsilon times n to the power constant, and this constant is independent. This exponent of n is independent of 1 by epsilon. So typical runtimes look like this: 2 to the power 1 by epsilon times n to the power 1000, or this 7 by epsilon to the power 1 by epsilon to the 1 by epsilon times n to the power 10 to the power 6. This is impractical, but this is technically better than the previous one, because it's a constant. So for very small epsilon, this value is much smaller compared to this value. But you will not have something like n to the power log 1 by epsilon, because this exponent is not independent of 1 by epsilon. So this is not an EPITAS, whereas the previous two are EPITAS runtime. And we'll see later there is something called W1 hard complexity class. If you want to show some problem is it does not have any EPITAS, then you have to show the problem is W1 hard. So under some assumptions, so this all these assumptions assume P equal to NP. This also assumes something called W1 equal to FPT, etc. But people believe these complexity theoretic assumptions are true, and under that, if you show W1 hardness, then that will imply there is no EPITAS. And then finally, the strongest one is called FPITAS, or fully polynomial time approximation scheme. It's again a PITAS, but runtime is order n cube by epsilon square kind of terms. That means it's polynomial in input size and 1 by epsilon both. So just compare these three: PITAS, EPITAS, and FPITAS. So PITAS has n to the power 1 by epsilon kind of terms, whereas EPITAS might have something function of 1 by epsilon which is actually exponential in terms of 1 by epsilon, but the exponent of n is polynomial. Exponent of n is constant, independent of 1 by epsilon. But in this FPITAS, it is polynomial in both in terms of n and 1 by epsilon. Okay. So these three notions will recur in the course. We'll study PITAS and FPITAS for some problems. And intuitively, FPITAS is the best you can do for a problem, because you will not have one approximation for the problem unless P equal to NP. So what is the best you can do? You can hope for this 1.001 approximation, and the runtime you want as small as possible. So runtime you want polynomial in n and 1 by epsilon. So that's kind of the best you can hope for. And we'll see later something called strongly NP hard problems. So to show some problem does not admit any FPITAS, we need to show the problem is strongly NP hard. So we'll come across these notions again later. Today we're just going over some definitions. We'll again repeat this definition later as well. But just to tell you the definition of approximation ratio, PITAS and FPITAS, these things we'll use many times in the course. I mean, you should remember these three definitions at least: approximation ratio, PITAS, and FPITAS. Any questions so far? Okay. So there is some more PITAS. One is called QPITAS, which is again 1 plus epsilon approximation, but runtime is not polynomial. this quasi-polynomial. So if you have not come across this term quasi-polynomial, it means some expression like this, n to the power log n to the power constant. So think of the polynomial case. So polynomial is n to the power constant. This is polynomial. What is exponential? It is 2 to the power n or something like this, some constant to the power n. So there is something intermediate between this and this, and quasi-polynomial kind of talks about this. So if you think of n to the power log n, you see that is already bigger than n to the power constant because the exponent is much higher, log n. Whereas if you compare this 2 to the power n, then it's much smaller, because if you take log of 2 to the power n, log of this value becomes n. If you take log of this value, n to the power log n, that becomes log n times log n, so log n square. So log n square is much smaller compared to n in the asymptotic case. So this is better than exponential, but still worse than polynomial. So for some problems, it's interesting to see if you can do something better than if you can do better than exponential time, polynomial time algorithm in slightly more runtime, in quasi-polynomial time, and get 1 plus epsilon approximation factor. And there is also something called p-pitas, which is again 1 plus epsilon approximation, but the runtime is pseudo-polynomial. And what is pseudo-polynomial? So as I mentioned earlier, this data B or numeric data, biggest numeric data that you have, h cost, etc. Normally we take log of that value as the input. So the NB term will be exponential. But if you assume this numeric data is given in unary, and if you have runtime like NB to the power constant, so runtime is polynomial in terms of n, but as well as polynomial in terms of b. So in general polynomial time, we want this to be polynomial in log b, but in this case it's polynomial in b. Then we call it pseudo polynomial time. It's not polynomial time, but it's still not too bad. So if we have some algorithm which is giving 1 plus epsilon approximation in this runtime, we call it pseudo polynomial time approximation scheme or p-pitas. So these two notions are also required. Now, one reason people study these kind of things is if you prove some problem admits q-pitas, then under some complexity theoretic assumption, it implies that the problem should have a pitas. I mean, we don't have the algorithm, but we believe that the problem should have a pitas. So that's the reason. I mean, if you want to show the problem is easy to approximate, you show the problem admits a q-pitas. That kind of imply you should have a pitas in future. So these notions, q-pitas, p-pitas, or quasi-polynomial time, pseudo-polynomial time, you have to remember. Any questions so far?
Excuse me, sir.
Yes.
Sir,
Yeah.
I remember correctly, you said that n times b running time is equivalent to exponential, right?
Yes.
So now you're saying nb to the constant is also called pseudo polynomial. So that is also exponential, isn't it?
Yes, it's exponential. It's not polynomial, but I mean the point is exponential could be something like this as well. 2 to the power n times b. This is also exponential, but this is not pseudo polynomial. So this is exponential. This is also exponential. It's not polynomial because in general it is log b to the power some n. So in terms of b, it's polynomial. In terms of log b, it's exponential. So it is still exponential. But the point is, it's slightly better than general exponential in general. So it's a subclass of exponential time, but it's better in the sense that there could be exponential time algorithms which are exponential in terms of n as well. But for pseudo polynomial time, it is polynomial in terms of n, but exponential in terms of log b.
Okay.
Is it fine? Yeah. So this is both are exponential, but it is slightly better because the runtime is at least polynomial in n. So for some problems, if you have b to be small, maybe you know that the problem has h cost only up to 1 to 10. Then b is already constant. Then pseudo polynomial is good because then it's just a polynomial because b is constant, for example. Whereas for other problems, if you have 2 to the power n times b, that's exponential. There, even if b is constant, it's still exponential. So yeah, this paragraph talks about some things. I'll just go over briefly, but we'll come across this later. I just wanted to go over these notions of pitas. So pitas is a class of problems which admits polynomial time approximation scheme, and APX is the class of problems which have a constant factor approximation. So you can think of P and NP kind of classes. Again, we defining something like those classes in terms of approximation. And as we have NP hard, that means the problem is as hard as any problem in NP. We have something called APX hard. That means the problem is as hard as any problem in APX. So in case of NP hardness, there is something called polynomial time reduction, but here there is something else called p-test reduction, etc. But for now, forget about these things. We'll come across this later. But the main thing is APX hard is a hard class, and if you have a problem which is APX hard, then you should not expect a p-test for the problem. And similarly, if you have a problem for which you have q p-test, then the problem is not APX hard, so you should expect a p-test for the problem. So these two notions you should remember. Other things is L reduction and other kind of reduction we will come across later in the course. But this too will be interesting fact to remember, that if the problem is APX hard, it has no p-test. Even if it has a q p-test, then it is implying that the problem is not APX hard. So now some more definitions. So we'll again repeat these definitions later, but just I wanted to go over all the definitions before we start. So we talked about absolute approximation earlier, the general approximation ratio. And what was that? There was this kind of a ratio. So you look at all instances I, and supremum or the maximum you take of AI by opti. So AI is a solution by the algorithm, and opti is a solution, is the optimal solution on input I. So that's a way of thinking of approximation algorithm. Now think of two algorithms, okay, A1 and A2. So for one problem, you have actually guarantee like opt I plus 1 for all instance. In other instance, you have guarantee like 2 times opt I. So which one is better? You'll say, okay, in terms of approximation ratio, if you look at absolute approximation, both are kind of similar, because the worst case approximation ratio for both of them is 2. And this is attained for this particular problem when opt equal to 1. Then you have A1 I equal to 2, the ratio is 2. And for this one, it's always 2. So they are both similar in power. But if you think this is actually much better algorithm in general, if you have larger opt, let's say opt equal to billion, then this is giving you billion plus 1. The ratio is basically billion plus 1 by billion, which is almost close to 1. So when opt goes to infinity, this actually goes to like 1, the approximation ratio. It's much better. So to handle this kind of pathological cases, where the ratio is quite bad for small opt, but it's actually good for larger opt, we introduce something called asymptotic approximation ratio. So in computer science, we talked about asymptotic runtime. So this is also a good notion to consider in the asymptotic sense. So what is asymptotic ratio? Okay, there is some complicated term. We'll go over them. So let's parse this one by one. So first look at this quantity. What is it saying? It's saying the ratio of AI by opti, basically for input I, what is the ratio of the algorithm solution and optimal solution. Given optimal solution is n. Okay, this is the condition. And then you look at all possible such input and look at the ratio, that is called this rho an. So basically for all instances with optimal value equal to n, you look at what is the worst case ratio that the algorithm provides, that's this value. And then you look at the limit of this value, lim sup of this value. What does it mean? As n tends to infinity, what is the worst case value of this term? Okay. So that is what the definition of approximation asymptotic approximation ratio. In other words, what it's saying is when n tends to infinity, basically you can think of opt is very large. In that case, what is the ratio we get here in AI by opt? Worst case ratio that we get. So think of one example. Let's say the runtime is like alpha times opt, not runtime, the approximation guarantee that you get is alpha times opt plus some constant like this. So then what is the approximation ratio? As opt grows and goes to infinity, then this constant is very small compared to opt. So you can actually ignore the constant and just focus on the opt, and the ratio you get is alpha. So in this case, the asymptotic approximation ratio is alpha. In fact, it is true even it is something like small o of log opt. Because if it is small o of log opt, then this is again much smaller compared to opt, as opt tends to infinity. So you can ignore that part and you get the ratio to be alpha. So when you talk about some algorithm and say it has alpha asymptotic approximation, that means it has a guarantee which is alpha times out plus some constant. For now, you can assume a constant. Okay, so the previous algorithm that we talked about is op plus 1. It's actually having asymptotic approximation ratio of 1, whereas the absolute approximation ratio was 2. And we'll see for some problems why these notions are important. So when we study a problem called bin packing, we'll come across these notions. Okay, finally, I will talk about this different kinds of inapproximability. So as I mentioned that NP problems are kind of equivalent in terms of decision variance. So if you solve one problem, all the problems are solved. But in terms of approximability or approximation ratio, the optimization versions could be quite different. So this is a survey by Arora and Lund in '96, and they showed that all these problems can be kind of classified into 4 broad classes. So for some problems, you will get any approximation as possible. For some, like pitas, f-pitas kind of thing, and for some problems, you will not get anything. So even 1 plus epsilon approximation is hard. So one example is max 3 set. We'll see. Then some problems like set cover, it's even difficult to get an approximation which is order better than log n approximation. Then some problems which are there like level cover for which this kind of approximation ratios are difficult to obtain. And then some other problems like click are there for which even n to the power epsilon, for where epsilon is a constant, is difficult to obtain. And based on that, they define these 4 classes and the relationship is given here. So easy among this, as you go along this line, it becomes more and more difficult. So max cut is easier compared to set cover or click, for example. And this table talks about some examples where a lot of problems are mentioned for which it's difficult to get pitas or f-pitas, and then some problems for which it's difficult to get better than log n approximation, and so on. So it's just for your knowledge, just to see the problems can differ in terms of inapproximability. And we'll see as we go along for different problems, we'll show in different inapproximability guarantee for different NP-hard problems. So finally, it looks like this is containment. This class called P. P is here. Then f-pitas is enclosing P, then e-pitas, then pitas, then APX. APX means the problem has constant approximation. The algorithm has the problem has a constant approximation algorithm, and then you have APX even outside of this. And all these containments are strict if we assume P not equal to NP. Now, okay, so now we talked about P not equal to NP. Under that, we study approximation. But is it really the case? What if one shows P equal to NP? Do you still need approximation algorithms? The answer is a resounding yes. The reason being this. So optimization problems can be hard for multiple reasons. Interactability is one of them. So NP hardness is one of them. But apart from that, there are many other reasons. So maybe there is uncertainty. So you may not know the whole data in the beginning. So there is something called online algorithms which deals with this, which is a variant of approximation algorithm. So think of Uber or Ola taxi allocation. So there are people who are coming, and Ola or Uber has to assign a taxi to the person, but they don't know who are the future people, future customers that will arrive. So based on this incomplete knowledge, they have to take a decision. So that's again, they have to take some approximation here. They cannot find the optimal solution because they don't know the whole input. So can they do some kind of approximate solution, which is good. Or you can have dynamic input. So data can change over time. So let's say you have a graph, some kind of computer networks, and some of the links can get created and deleted over time. So what you want is your solution is changing over time, and you don't know what will be the changes over time. You want to maintain a good solution with small changes. There also you need. It's difficult to get exact algorithm, so you go for an approximation algorithm. Or sometimes you have too much data, big data, and the data array is very fast, and it's really big, so you cannot really store the whole data. So you cannot really solve it exactly, but you can probably do some. You can store some small amount of data and still do some approximate solution. So these are there, and also other problems are there. For example, there is some area called fine-grained complexity. So there are some problems like, let's say, longest common subsequence or edit distance, which are solvable in order n square or n cube kind of time. But exactly you need order n square or n cube time, but maybe in practice you need a linear time algorithm. So then you cannot really solve it in polynomial optimal solution you cannot get in order n time, but can you get a good approximation in sub-quadratic time or sub-cubic time? Then there is distributed algorithms, parametric algorithms. So all these problem areas where you are not able to get optimal solution, you look for approximation algorithms. And the techniques that we study in approximation, they are kind of general. So the techniques, let's say for approximation algorithm like LP duality or primal dual schema, they're also used in online algorithms or dynamic algorithms. So these techniques or randomized rounding, those techniques are used in streaming algorithms and so on. So these techniques are very general and generic. So if you learn these techniques, you can apply to other algorithmic paradigms as well. So what are some techniques? So I'll go over some techniques just to mention that we'll cover in the course. But yeah, the details are there in the website, and we'll learn many of these techniques. So some techniques you already know probably from your undergrad class, but you'll see, like say greedy. Greedy you have probably studied in an undergrad class or dynamic programming. But there the goal was to get exact solution using these techniques. But here you'll see how to kind of get good approximation algorithms using these techniques. Then there is local search, then commutative algorithms, which will be based on some other properties. Then we'll use something called rounding of data. So you have some data and there are too many different types of data which is difficult to handle. So you do something called rounding where you replace the original input by some other input, modified input, which has less number of types, and that will help us to solve the problem. So these are the techniques that we learn, some of the techniques. And then there is also cuts and metrics embedding kind of techniques for cut problems we'll see. For geometric approximation, we'll see some computational geometry problems and approximation algorithms for them. Their techniques are slightly different, like geometric separators, shifted grid, quad tree, etc. And then there are some other powerful tools, maybe you have not heard in undergrad algorithms. One is linear programming. So we'll see we can propose algorithms based on linear programming. Something called deterministic rounding, randomized rounding, etc. etc. So basically, we'll see, I mean, all these problems which are NP hard. So integer programming is an NP hard problem. So all these problems can be reduced to integer programming. And then linear programs, we'll see it's a relaxation of integer program, and linear program can be solved in polynomial time. So you solve a problem using linear program, but you don't get a solution which is integral. You get a fractional solution, and you do some operations to get an integral solution. So for now, it might sound vague. We'll see what are these things called fractional solution, integral solution, etc. But this is a very powerful technique that has been developed in this area, and it has many use, many problems. Then we'll see some other techniques called semi-definite programs, which is even generalization of linear programs. So linear programs basically talks about cases where, okay, in optimization problems, you are selecting some items or you're not selecting. It's a 1 or 0 decision. In linear program, you have it's a real number between 1 and 0. In semi-definite program, it becomes a vector, and then based on that, you do some algorithm design. And there are more advanced techniques like hierarchies or sum of squares. Some of these things will be covered in the class. We'll also talk about hardness of approximations. How do you prove some problem is hard to approximate? You cannot really get better than this factor. So for that, there are techniques like approximation preserving reductions, PCP, level cover, unique games, and etc. And these are very mathematically rich things, PCP and unique games. We'll again talk about this in the later part of this lecture. Okay. So any question till now? Fine. So in the rest of the lecture, I'll talk about mainly the history of algorithms, approximation algorithm, how this field was developed, and who are the initial founders, and what is the status of the present state of the art, and so on. So this area was started by Ron Graham. So those of you who attended Theories Toolkit, you may have come across this Ramsey number and work of Graham. So Ron Graham, he studied a problem in scheduling, and he gave the first approximation algorithm. So Ron Graham this is a picture of Arindam with Paul Edosh and his wife Sanchun. She has done a lot of work in spectral algorithms and one of the leaders in discrete math. And Edosh, probably you already know, there are a lot of stories about Edosh, the man who loved only numbers. So, okay, what is the problem that they studied first? Graham. So he said this problem. It's a scheduling problem. So you have some jobs. There's a J1 to Jn. There are n jobs, and each job has some processing time pi, and there is some relationship between the jobs. So what does it mean? It means, okay, input job is like this, and if we have this relation like arrows, that means I can only finish a job. I can only start a job JL after all these other jobs on which it depends are finished. So arrow means that this symbol means that GI has to be finished before JL is allowed to be started. So think of some jobs like I don't know, maybe some kind of cooking kind of case. So you have to first cut the vegetables, then only you can do frying, and then probably you have to add spice, etc. So there is some step-by-step process you have. So there is some dependency, or some other kind of scheduling where it's in some CPU you're assigning some jobs, but maybe you need the output of a job to be required for the input of the next job. So that kind of relationships are showing that thing. So what's your goal? Your goal is to find, okay, so one thing is you want this non-preemptive schedule. So if you start the job in a machine, you cannot stop it. You have to complete the job, then only you can start a new job. It's not preemptive, it's non-preemptive. And you want to schedule all these jobs in M machines. So this should be jobs. And your goal is to minimize the make span. So you want to make span means the longest time taken by a machine. So in this assignment, for example, these machines are being used. There are 3 machines, m equal to 3 in this case, and jobs are assigned like this. So basically, as you see, all the jobs are starting after all the previous jobs on which it was dependent, they are finished. And then this is the end time of these jobs. This machines, this is the end time, this is the end time, and this is the end time. So we take the maximum of this value, and this is called make span. So your goal is to finish all the jobs as quickly as possible. That's called make span. And this is also known as this kind of a notation, P, PI, precedence, and Cmax. So this area of scheduling is, there are multiple textbooks on this topic. It's a very well-studied area, and there are a lot of different notations. So for example, there's a website called Scheduling Zoo. If you go there, then you'll find out these notations, and they are defining very different types of scheduling problems, and you will see what is known about these problems and what is not. So let's P is called identical, Q is called R is called unrelated, and so on. So we'll talk about them later, but just to point out, if you want, you can just go there and see what these things are meaning. And precedence means this kind of constraints, precedence constraints. And then there is an objective function Cmax, which is this make span, maximum completion time basically. And there are some other variants. You can take the sum of this weighted completion times and so on. So if you're interested about learning about scheduling, then you can just visit this website and see. So this is the first problem he was studying, and he found, okay, it's difficult to find a exact algorithm for the problem. So what he proposed, a simple greedy algorithm. So you can actually think about the algorithm, like what can you do? So what you can do is probably, if you have some available machine and there is some job you can schedule, so all the previously needed jobs are finished, then you can just assign it, right? So that's the most simple algorithm that you can do. So Graham proposed that algorithm. So for time period t equal to 1 to continue, if there is some idle machine which is available and all the predecessors are already finished, then you schedule the job. So basically, this is the bottom line, that at any time just start a job whenever it's possible. This simple algorithm is short. It is actually giving you a 2 minus 1 by m approximation. So we can always show this list scheduling. We'll find a schedule with this make span, and you can actually show it's tight. So there is some instance for which this is giving you 2 times 2 minus 1 by m times opt make span. And it's not too difficult to see the analysis idea. So let's one slide. This is just showing a proof of 2-opt. So let me pause for a couple of seconds and then I'll go over the proof. Okay, so the proof is this, that let's consider some sequence of jobs, J1 to JK. And JK is the last job of the whole schedule that finishes. So maybe this is the last job. JK finishes, this is the max span that we have. So what properties can we have? So one thing is, okay, JK, there is some kind of a, it has dependency on some jobs. There's some partial order that is there. So J1, then J2, then this is and this. So JK was dependent on some job and then so dependent on some other job and some other job and so on. So if you have this kind of a chain, and let's say Ji is the predecessor of Ji plus 1 that finished last. So we J1, J2, this way we did. So then after Ji finished, Ji plus 1 was started as soon as a machine is available. So if we are not able to assign JK just after this job is finished, that means all the time period before this, the machines are completely busy. Otherwise, I could have scheduled JK here itself. So machines are already busy, so I could not schedule JK here. So what does it mean? That means length of all busy period, it has to be less than equal to opt. So opt is, so okay, one point is whatever way you schedule, you have to schedule J1 and then J2 and then J3 and JK and so on. This is actually a lower bound on opt. And what we are saying here, this length of this chain, J1 to JK, it has to be less than equal to opt. That's what I'm saying. That if you want to schedule all the jobs maintaining this precedence constant, then you have to schedule all the jobs in the chain, and that will actually require at least the length of the chain that is less than equal to opt. And as it was busy between all the intermediate time period, so length of the busy period, that means total whatever jobs were there, they cannot schedule less than this busy period. Because this busy period is already completely busy and we also have still some more jobs. So length of busy period has to be less than equal to opt. So what is the max span then? It's basically the length chain and you add this busy period. Both of them are less than equal to opt. So total time is less than equal to 2 times opt. So that's the way you prove. So for this, as I said, like the opt is already, it's an NPR problem. You don't know how to compute opt. So for this problem, then we think about some better lower bound. So one lower bound we found on opt was this chain length. So whatever this J1 plus J2 plus J3 plus JK, this is already a lower bound on opt. You cannot have opt less than this value. Also, this busy period is completely occupied. So if you want to schedule all the jobs, you have to at least use this many amount of time period. So the busy period is also less than equal to opt. So combine this two fact, you get it's less than equal to 2 times opt. So it might be a bit difficult to follow because the first analysis, but if you have any question, please let me know. Okay. So just go over this lower bounds. Why length of busy period is less than equal to opt and why length of chain is less than equal to opt. Then the proof will be clear. So basically we are decomposing this solution that we get, the algorithmic solution, into two regions. One is this green region, other one is the busy period region. And both of them are lower bound on opt, and this algorithm solution is this busy region plus the chain region. So you get two approximations. And actually, it was shown that this is the best kind of you can do. So for any fixed epsilon, you actually cannot get better than 2 minus epsilon approximation under something called unique games conjecture, which we'll see later in the course. And actually, this problem it's received so much attention. It's more than 50 years. It's from 1966. It was started. So when he was working in Bell Labs. So more than 56 years or 55 years. But still, this problem is not very well understood. So in the sense, even this question is open. So if you have only 3 machines, so P3 means only 3 machines, and Pi equal to 1, So that means all the jobs have unit processing time. Then and if precedence constant, then what is the best you can do? So there is a 4/3 approximation here, but it's not known if you can do better than this or not. So the difference with this previous one is was for general M. So number of machines was not constant. Here number of machines is only 3, and also it was for general processing time. Here it's same processing time for all the jobs. It's PI equal to 1 for all. But even in that case, 4/3 is the best one. And in fact, it could be possible this problem is polynomial time solvable. So it's not known whether this problem is NP complete or it's in P. So it's one of the top open problems in this book by Carey and Johnson, for which don't know whether it's polynomial time solvable or it's NP hard. Okay, so this is the first problem that people studied, and the area of approximation algorithm was started, and then it saw rapid progress. So next, people found that, okay, as I mentioned, that optimal solutions, finding it is already difficult. It's an NPR problem. So what can we do? Can we use some other problem, which is polynomial time solvable, and use the solution of the polynomial time solvable problem to get approximation of other problems? So what people found that there is a problem called traveling salesman problem, which we'll see later. And people found, okay, this is already NP hard because it's a generalization of this Hamiltonian cycle problem. But you can take minimum spanning tree problem, for example, and that's a polynomial time solvable problem by Prim's algorithm or Kruskal's algorithm. And you use that solution to give a solution of TSP, and that is not too far. It's a two approximation algorithm. So we'll talk about this in detail in next week's lectures. So this is the first time people showed, okay, I cannot solve the problem exactly, but I can use some other polynomial time solvable problem and use it to get approximation algorithm for this problem. Then Graham studied more. So he studied the scheduling problem again, but now without any precedence constraint. So you can schedule jobs as you wish. There is no precedence order in there. And there he proposed an algorithm called longest processing time. And he showed it's a 4/3 approximation. So basically what you do is, given all the jobs, you sort them according to processing time, and the longest job you first assign, and then the second longest job, and you continue. And what he showed is you can do much better. Actually, there is another algorithm devised which gave the first polynomial type approximation scheme. So given constant number of machines and some constant epsilon, he showed that you can get a solution by that algorithm, which is 1 plus epsilon times opt. The runtime is something like this. So for m constant and epsilon constant, this is a constant. This part is constant. So you get order n log m time algorithm. So this is the first PITAS he found. And then in 70s, we saw more progress. So this area of NP completeness came. So Cook and Levin first proved that. So before this point, actually, they are trying to solve this problem, but they did not know whether the problem can be solved easily or not. They were not able to find an efficient algorithm, so they found some approximation algorithm, but there was no theory, proper theory that why it was hard. But then in 70s, people came up with more theory. So first Cook and Levin showed that Boolean satisfiability is NP complete. Then Karp showed this 21 famous NP complete problems. And then Gary and Johnson wrote this book, famous book, which showed most of the practical problems are NP hard. So people studied, I mean, they found, okay, these problems are NP hard and we don't expect exact algorithm for them. So we have to solve in some other way. So people focused on approximation algorithms a lot. And David Johnson played a great role here. So he wrote his thesis on bin packing problem, and he used the term approximation algorithm. Previously, people did not use any name for this. They gave a guarantee 2 times opt or something like that. But the term approximation algorithm or approximation guarantee, it was coined by the thesis of David Johnson. Then people did even further progress, and they showed FPTAS, a fully polynomial approximation scheme. So for knapsack problem, Ibarra and Kim showed that you can actually go beyond PITAS, and actually you can get an algorithm which is polynomial in n and 1 by epsilon. And then so previous one, for example, what we showed, it was not polynomial in 1 by epsilon. So Ibarra and Kim, they showed that it's actually better than that, and you can get polynomial in n and 1 by epsilon. In fact, we'll see a variant of this algorithm which runs in time n cube by epsilon in next week's lecture. And then there was a famous algorithm with Christophides, which gave 3/2 approximation for traveling self-learned problem. We'll again see it next week's lecture. And it remained the best algorithm for almost more than 45 years. Only last year there was a breakthrough on this problem. People gave 3/2 minus 10 to the power minus 36 approximation algorithm. A slight small dent, but there was a big breakthrough, and it was the best paper award in. It got the best paper award in one of the top conferences in CS. And then on the other hand, people try to prove hardness, that why some problems are difficult to approximate. So Sahani and Gonzalez showed that some problems like TSP, if you look at the general variant, you'll not be able to get any constant factor approximation. So they showed that if you get a good approximation for a problem, that's equivalent of getting the optimal solution of an NP-complete problem. So that developed this area called theory of inapproximability. And then people like Osceola and others, they developed this approximation preserving reduction, and they defined APX and other classes, and this area got developed more. Then in 70s and 80s, people saw more breakthrough in other type of algorithms. So linear program became prominent. So people were using linear program from this World War time itself for scheduling and other things, but it was using simplex method, which was exponential time. It was not polynomial time. And it was a big question whether LP is in P or not. So Khachiyan in 79 gave ellipsoid method, which showed actually you can solve linear program in polynomial time, but it was kind of impractical. But then Narendra Karmarkar gave interior point method, which showed more efficient and polynomial time, somewhat practical, more practical algorithm. And then Groschel, Lovas, and Stryver, they showed optimization equal to separation. So to solve an LP, what you need to do is basically given an LP, if you give a point and if you can separate the point from the LP polytope, then you can solve it. So these are kind of jargons I'm talking about, but this is the way people are progressing one by one, and people are developing more powers for linear programs. And this was then was very useful because integer programming was NP hard and linear programming was a good approximation for integer program. So people could solve linear program and use that to obtain good approximation algorithm for other problems. So we'll talk about integer program in detail in 2 weeks or 3 weeks of time. Then it will be more clear. But these techniques were very helpful. So first, people study set cover problem, which will be the first problem that we'll study in the next class, and gave order, log, and approximation algorithm. So there are multiple people who gave simultaneously, independently this algorithm: Johnson, Lovas, and Quatal. And then Hochbaum gave F approximation, where F is the frequency of an item. So it's technical term again, but my point is there are different techniques which are being developed using linear programs for set cover problem: deterministic rounding, randomized rounding, then primal dual, and so on. So Raghavan and Thompson developed this area of randomized rounding, where people use randomization to round. By round, it means convert a linear program solution to a integral solution. And then people study this asymptotic approximation ratio, and for bin packing problem, De La Vega Luker gave asymptotic pitas, and Karmarkar gave asymptotic F pitas. And again, this was a big breakthrough in this area. It developed some new techniques called iterative rounding. This was again open for more than 30 years, and only 2013 or 14 people could improve it further. And then in early 90s, there was more breakthrough. So semi-definite program came, which is generalization of approximation algorithm, and it's very elegant. So we'll see in the class. It's a very simple algorithm that you give a problem and then you look at some kind of a circle or sphere, and then you take a random hyperplane and get solution based on that. So it's one of the most simplest algorithm that you will come across. But strangely, it has rich connections with many problems in unique games conjecture and many other areas. So in fact, this max cut problem we'll also see next class. It's very trivial to get half approximation, but it can be shown that if you use in any of these techniques, you will not beat half. Only 78 programming could break this barrier of half, and you could get. I wrote it 0.878, but basically 1 by 0.878 approximation factor that we can get, and it turns out it's actually optimal under some assumption of unique games conjecture and so on. It's a big breakthrough. It has many elegant theories, and like a lot of awards people got because of this breakthrough. So then this other area got started in approximability called PCP theorem. It's one of the most counterintuitive theorems that you will come across. So just read this part. What is the statement of PCP theorem? Okay, so what it says is for there is some universal constant k, let's say 1000 or something, such that for every n, if you give a mathematical proof of length n, then you can convert it to another proof, which is again polynomial in n, and then you just check k number of bits in the proof. So the proof can be 10 to the power 1000 or very large number of it can have large number of bits. It's basically not a constant, it's an n. So it could be huge, very large, but you can only check 1000 number of bits, even less, let's say 3 bits you can check. And based on these 3 bits, you can maybe do some kind of parity operation or some other operation. And based on these 3 bits, you can say with 99% accuracy whether the proof is correct or not. So it seems like it's impossible, but that's one of the most counterintuitive theorem that we have in computer science. That given any arbitrary proof of length n, you just verify 3 bits. Like you just go to location, let's say 1000, 2000, and 5000, and see what are the values are there. Like it's a bit, like 1, 0, and 1 maybe. Based on these 3 bits only, you can decide with 99% accuracy the proof is correct or not. And this was a huge breakthrough, and it required a lot of new mathematical techniques and ideas. And the Gödel Prize, for example, which is one of the top prize in theoretical computer science and discrete math, it was awarded to Sanjeev Arora, Madhusudan, Rajiv Motwani, and others for this PCP theorem and its connection to hardness of approximation. So people devised this theorem and showed that using this theorem you can show hardness of approximation for many of these problems. And then again, the original proof was very long. It was more than 100 pages. And Edith Dinur found a somewhat simplified proof in PCP theorem. And she again got Gödel Prize for that. But even that is quite complicated. So when I was a grad student in Georgia Tech, Prasad Raghavan taught a course on this topic. And I think 8 or 9 classes were just on this proof of PCP theorem, even for the simplified proof. Even that was quite complicated. Yeah, so here let me talk about these guys. Like so Sanjeev Arora was AIR 1 in IITJE in 1980s. He's a professor in Princeton. He has made a lot of breakthroughs in computer science. Probably one of the candidates for Turing Award. Rajiv Motwani was one of the mentors for Google. Sergey Brin and Larry Page, or Larry, yeah, that's the name. And Madhusudan also, he's a professor in Harvard now, made a lot of breakthroughs in different areas. And then this area saw a lot of progress. And in 2001, the first textbook came by Vijay Vazirani. And then other people, like I already talked about this guy, like Umesh Vazirani is another key person in this area, brother of Vijay Vazirani. And then Sahani and Konjala, they talked about the inapproximate result, Sataj Sahani. Narendra Karmarkar, another AIR one in IITJE, he developed this linear interior point method for linear program, and also Karmarkar algorithm for bin packing and so on. Prabhakar Raghavan started this area of randomized rounding. In randomized algorithms, we actually read the textbook by Raghavan and Motwani. So Raghavan and Motwani. So this also, due to this connection with PCP and other areas, there are a lot of other insights which were gained. So for example, Subhash Khote, he got this Rolf Nevinlinna Prize in 2014. He's another AIR one in IITJE 1994 or 95. So he got the award for this thing, for definition of unique games conjecture, unique games. So basically proposed some problem and gave some conjecture and showed connection of that problem with many other problems. So that is his contribution. He got this award. So Nevinlinna Prize is like Fields Medal for computer science. Under 40, it's given one time in 4 years. So yeah, if you search in YouTube, you'll see videos on this topic. So what is unique games and what was his contribution? So one thing is this area saw a lot of Indians. One reason is Vijay Vazirani was a professor in IIT Delhi, and a lot of students from IIT Delhi started studying approximation. And overall, I think if you see any Indian computer scientists, almost all of them have worked on approximation at some point of their life. So some of these guys are here. Moses Charikar, he's in Stanford, R. Ravi in CMU, Anupam Gupta in CMU, Shuchi Chawla in Texas. So these are like like Charikar worked on cuts problem, for example. R. Ravi had a textbook on iterative rounding. Anupam Gupta, he is probably the best speaker. I mean, if you go to his talks, he's a great speaker. Suchi Chawla, she worked on network design kind of problems and game theory as well. Samir Kullar, he's also network design their breakthroughs. Kamal Jain, he made a big breakthrough. We might not study that problem here. It's called survival network design problem. Then even in India, we have Professor Navin Garg in IIT Delhi and Professor Amit Kumar in IIT Delhi, who are again pioneers in approximation algorithms. Chandra Chekuri in UIUC, Nikhil Bansal in UMISH, Venkatesan Guruswamy, I think he's leaving CMU now. Sanjeev Khanna in UPenn, Arvind Srinivasan in Maryland, Kunal Talwar in Google, Mohit Singh, Georgia Tech, Prasad Raghavendra in Berkeley. So all these guys made a lot of breakthroughs. So Raghavendra, he had a breakthrough result which showed that for any constant satisfaction problem, there is one single semi-definite program which can get the best approximation factor under unique games conjecture. Or Mohit Singh developed this area of iterative rounding. So there are a lot of breakthroughs which were made by these guys, by Indians. And this area remained one of the most fruitful areas in computer science. So if you look at the previous awards in CS and other areas, so think of Gödel Prize, which is again like Gödel and Fulkerson are the top prizes in theoretical computer science and discrete math. So, like for example, in India, we have this AKS probability test, which is not an approximation, but Agarwal, Kal Saxena, they got this prize, which was the biggest breakthrough from India probably. But if you look at the other awards, like Sanjeev Arora and Michel got a prize for PITAS or for this Euclidean TSP problem, or Hastad got this prize for inapproximability of for other problems, and so on. So Irit Dinur got for PCP theorem, also for other PCP people got, but it's not mentioned here. It's before this. Fulkerson, Gomez and Williamson, I mentioned about this max cut algorithm for semi-definite program, they got that award. Or Jerome Sinclair, Vigoda got for approximating the permanent. Arora Rao Wazirani got for approximating fastest cut problem and so on. And even if you look at recent activities in theory CS, so this is a conference called STOCK and it's called FOX. These are the top two conferences in theoretical computer science. Even the best paper awards there, a lot of approximation papers. So for example, last year, this big breakthrough came where people improved this 3x2 approximation for TSP to 3x2 minus 10 to the power minus 36. Very small dent, but using a lot of new techniques. So that got one award, and then even for other variant called asymmetric TSP, there is another best paper award here. So all these papers are mentioned in the website. If you go to project topics, you will see these papers. They are quite long, so I don't expect you to understand everything, but you can see if you like them, then you can start reading them as well. And similarly, in Fox, there are papers which talks about approximating edit distance, online bipartite matching, polylog approximation of other problems, and even for TSP, if you see this is a TSP paper, TSP paper, TSP paper, and this is unique games paper, and so on. So there are a lot of papers in this area. So one point is last year actually this paper, which got best paper award, was by Nutan Limaye and Srikanth Srinivasan and Sebastian Tevanas. And Nutan and Srikanth were faculty in IIT Bombay, but now they're in Denmark. This is one of the again landmark results which came from India. So yeah, this is, I guess that's it for today. There are some nice comics and cartoons you can see for this thing. So I'll share this notes and you can go over this comics. Okay, fine. So any other questions? Let me go to the
small question actually.
Yes.
The PCPTM, you said that the proof can be something like rewritten into another proof of length poly of n or something. Is the exponent there like, I mean, is it like any proof there is some polynomial thing, or is there some effective exponent there? Like at most n cubes there.
K, I think it's a function of K. How many bits you are supposed to read? It depends.
Yeah, you said that K equal to 3 is possible, right? For example.
Yes, for K equal to there is a constant. I don't remember the exact number. So yeah, there is n to the power billion or something, some large.
So there is some effective constant, fine.
Yeah, but it's a constant. It's a polynomial constant. From n you get n to the power constant. It's polynomial conversion only. Okay, so those of you who joined late, this is the team join code. So just join using this team join code. And I have already posted first 2 weeks of video lectures and lecture notes. So the next lecture is basically on set cover problem. So and max cut problems. We talk about greedy algorithms for set cover and randomized algorithm for max cut, and based on that we show another greedy algorithm and a local search based algorithm for max cut. So that is a single lecture for this week, and so I'll have a doubt clearing session on Thursday. So you can go over before that and we can discuss on Thursday. And I have also posted week 2 video lectures. You don't have to go it this week. You can go over the weekend or next week. So next Thursday, not this Thursday, next Thursday we'll have doubt clearing session for that one. So there first we talk about TSP problem, give a 3x2 approximation using this crucified algorithm. Then we talk about Steiner tree problem and give a 2 approximation for Steiner tree. And in the other part of the lecture, we talked about knapsack problem, give a FP task for knapsack, and bin packing problem, give an AP task for bin packing. So all these are for next week. So there are two lectures effectively. So there are 5 or 6 chunks of video that I have posted there. Totally, it will take 2 hours. So this set core video is I think 1 hour. For this week's video, it's 1 hour. So you can pause or you can listen 2 times speed or something. And next week's ones are 2 hours total for 2 lectures. So we'll meet again on Thursday to discuss more on the doubt clearing session on the first week's lecture. So you can go over the first week's lecture notes and the video lecture before that. Okay, there is some question, Sarvagya.
Yeah, so I wanted to ask, will it be possible to change the timings?
So that we have to see. I mean, it's not yet clear. I mean, I am fine with changing the time. The problem is, I don't know how many students are there, and always when we try to change, there is some problem. So for now, I think the first few weeks anyway, it will be online. It will be recorded. So probably you'll not have a problem. But I am fine with changing. So once we have a stable number in the class, then we can decide on the class time based on people's availability.
Thank you.
Any other question? Okay, if not, then let's meet on this Thursday at 11:30 for the first doubt clearing session for first weeks of lecture. Okay, thanks. Bye.